I'm going to tell you about a type of electronics that we're trying to build in my laboratory. We call skin-inspired electronics. So I want you to look at your skin and feel your fingertip. Well, our skin is capable of sensing the surroundings and send information to our brain. So that's what we want to mimic using our electronics. And skin is incredibly complex. So if we are able to do that using science and engineering, then that means potentially we can change how humans interface with electronics. But also we hope that could allow us to better understand our health and be able to monitor our own health. So we have electronics everywhere, information all around us. And our electronics is already so advanced. But yet, if we look at today's diagnosis and monitoring devices and medical devices that are being used, they either don't provide enough information or they don't really compatible with our human body. They're rigid and bulky and very difficult to be broadly used and really be used to especially inform us about our health. There's a big need to move beyond precision medicine, which is to come up with personalized treatment when a disease is discovered, but to move towards precision health, which is to monitor our health continuously and be able to discover a potential issue before that happens. So imagine the engines for airplane. We want to discover an issue before a catastrophic failure happens. So that's exactly what we want to do for human health. There's also a big need to really understand how all the different signals, information, electrical information, chemical information that really governs human health and how they really impact each other. And this is the information that's generated at cellular level, which is only tenths of micron, smaller than the width of human hair, all the way spread over even meter scale. So that means we need electronics that are able to measure information at high resolution over large area, and also in human without interrupting any of our everyday life. But we cannot do that because today's electronics are still made with rigid and brittle materials. And what we envision is to have electronics that are comfortable, invisible, imperceptible, biocompatible, and be able to measure information autonomously. So that's the electronic skin that we are trying to build. As a chemist, I wanted to build this from ground up, from the materials, because the electronic materials that we need to build these things, they did not exist before. Trained as a chemist and now a chemical engineer, we need to think about how we can come up with materials that are as soft as jelly, but have the electronic property as good as those used in our integrated circuits that are being used. So that's the big challenge we try to overcome. And also from molecular level, these molecules that from the conventional wisdom in designing either electronic molecules or rubber band type of materials, their requirements are completely opposite from each other. So we have to figure out how we can come up with a creative way to design this new generation of materials that address the challenges of one case, we want molecules to be rigid to conduct electricity. On the other hand, for rubber band, we want them to be very, very flexible. So we had a discovery that was really important now for us to be able to really put skin-inspired electronics on the map for new type of electronics. That is, we found ways to make these molecules not only be able to conduct electricity effectively, but we found also a way to make them into bundles so that they can not only transport electrons more efficiently, but also at the same time, we can incorporate things such as stretchability, biodegradability, self-healing properties, all into the same electronic materials, whether they are semiconductors or conductors. Now we have a variety of such materials available. And since I like to make molecules, I like to showcase this molecule here. To make the conducting polymer stretchable, we design special molecules that have these ring-like shape molecules surrounding them, so that when we pull these molecules, these circular-like molecules can slide around. And that's how we try to design these materials to be able to tolerate mechanical stretching and dissipate the mechanical energy without breaking. So with this kind of electronic material, we start to have electronics that we can measure information, not only from human body, also measure creatures that were not possible to be measured before. For example, this octopus, which moves around, but we are able to capture the muscle electrical signal from such kind of creature. And then with all the materials coming together, because we need a variety of them to build functional electronic circuits and functional displays. So this is a new form of display that now we can make using the materials we create. Imagine the screen that you work with. It can pop up or change shape when you touch it. So this could potentially be used to image our blood vessel when placing the sensors directly onto our skin. Let me show you some examples of the things we're building in the laboratory. This is a new type of skin sensor that's made of biodegradable and biocompatible materials. We spray on the material directly onto the human hand, and then we train it a few times. Then it will be able to recognize different objects. For example, these cones structure or cylinder structure or different kinds of shape. It can also be trained just with a few keystrokes to be able to, this is a virtual keyboard. It's typing on, and then the algorithm is recognizing the information from the typing. These are little mouse that's carrying the sensors that we build. The sensors and also the electrodes are continuously generating electrical signal to stimulate the healing of wound, but at the same time monitoring the progress of wound healing. So with this kind of device, we're not only able to make the wound heal faster and have lesser scarring, but also we can now start using this to understand what kind of genes get upregulated when we are able to perform this kind of treatment. This is something I'm very passionate about, that is to develop wearables that can allow us to monitor our own mental health. So this is first generation, still slightly rigid. Second generation, we hope to be much more skin-like, that incorporating various different sensors to monitor the state of our mental health. This is a newest sensor we developed. You heard about dopamine in first lecture. This sensor measures dopamine simultaneously in the brain and also in the intestine. So we actually give this mouse chocolate. Then we measured dopamine generation when the mouse saw the chocolate. And then when the chocolate get to the intestine, we were able to measure a spike of the serotonin that's generated in the intestine. And this kind of experiments never have been done before because the sensors typically, traditionally, they were too rigid to put into a behaving animal to be able to perform such measurement. Not only we're making the sensors to be soft, skin-like, but also the integrated circuits. They're important for the signal processing and wireless communication. So we're making our way towards really making the rigid wafer-like integrated circuits now to skin-like integrated circuits. We're making some progress towards translating our first generation of mimicking sense of touch sensors to now hopefully a product that can be, will be deployed in the intensive care unit for infant continuous blood pressure monitoring. So those are the skin-inspired electronics we're thinking about. And finally, I'd like to thank my research team. And it's really their creativity and hard work that brought us to where we are today, and so much more to do. And Stanford is really a place without a boundary. There are many, many collaborators who I work with. I'd like to thank them. And thank you very much for listening.